Elm architecture in Haskell, managing state with multiple threads, and it's a bit of a change of focus. So we've been seeing a lot of how to do different things, and I would like to change the focus to how can we keep it simple. Most of the time we are solving ordinary problems that have known solutions, and keeping it simple is very important. And I think a good way to keep it simple is using what Elm is using in the front end, which is what they call the Elm architecture. It's nothing more than a simple state machine, but it gives us some nice benefits. So by architecture, I mean a way to understand how data flows in our program, to organize how data gets changed, and how effects happen. So that's what I mean when I say architecture. So this is the Elm architecture. This is all of it. So the Elm architecture consists on having our program have some runtime that will take three main functions. A function to start our program, one to update our state, and one to view our state, which could be view it in the command line or view it in some graphical user interface. So it just having this architecture, we can already answer some questions very explicitly, like what happens in our program, how events get handled, where are they handled, and why do I have some change in my state. So I hope that we all convince you that this becomes very explicit. So usually we are offered a trade-off or more power at the expense of, at the cost of more complexity. So I hope to offer a solution that gives you less complexity at the cost of a much more rigid structure to our programs. So the whole idea is something very simple, which is what if we have all of our state updates be entirely defined by using one simple pure function. Now a pure function in a statically typed language is something very simple. We have the inputs here, we have the outputs, they are all concrete types, nothing fancy going on, nothing magic going on behind the screen. We have a message type which is defined by us and just represents all the events that may happen in our program, and we have our state, and then with that we should be able to come up with a new state and a list of actions to be performed. So let's go for our message type. Imagine that we are building a simple web crawler that, given a web page, will visit it, check for all of its assets and links, see if they are working, and if there are links in the same domain, it will visit that page, parse it, and do the same for all the links there as well. So we might be interested, if our page has loaded, so that we can process all of the URLs that are in there. So this is the URL of the page loaded, and the list of the URLs that was in there. If a link has loaded, so a link or a link to an asset, or if any of the two has failed to load, and we would react to those. So just by looking at this, we already see one of the great benefits of it, which is in this single type, we already have all possible events that our program is interested in and responds to. Now this is very useful for someone approaching our program for the first time. We can already have a good idea of what our program is up to just by having this type around. Now, before going any further, we must decide what our state will be. In the Elm architecture, we have only one state for the entire application. So before writing any part of the implementation, we must come up with a type that will contain the information that would, all information that we would care about for the whole lifetime of our application. We need to synthesize all of that in one type. So that is also valuable because we can use the type system to our favor. We can use the type system to make, invalid states impossible to represent, because we are using this one type to do that. And also, I argue that this encourages more thoughtful design, because you need to think about your state before starting to actually implement things. Now this is how the state of our web crawler would look like. We keep track of what the endpoints are that we are visiting, and we need to keep an HTTP manager around as well. And the status of any request that we are making might be loading, it might have succeeded or failed. Now this is our main. I changed our init type a little bit so that it takes an HTTP manager, and that's fine. So this is our initialization function. It just is very simple. The only thing that I'm not going to show you is how this function here is implemented, but basically it's just going to fetch something in a specific URL, and it will decide whether this is an asset or if it's a link inside the page, a link inside the same domain, and will pass the page and then throw the appropriate message, either a failed asset loaded or a page loaded. And so that's it. And I'm hard coding the website just so that we don't need to be passing it around. So, and this is our update function. If a page has loaded, we will handle it. We will check what we already fetched, what is new in there, and then we'll update our endpoints. And we will also fetch all of the new links that we have there. If a link has loaded, we just update our state, saying that it has succeeded. And if it failed to load, we also update our state. This is the entire program. This is all of it. There's nothing more to it. And already there, we can see another great benefit of this architecture, which is that we can clearly see a reason for each state change. The state changes are very well separated here. And if I want to wonder why is it that this failed value is getting into my state here, I can clearly see an English description that something failed to load. Why is it that I'm fetching more pages here? Well, because a page loaded and gave us some new information that we can use to perform this action. So it's more verbose, but it is very explicit, and there is great value in being explicit and making our programs easier to understand. You may also notice that we are returning a list of actions to be performed, but we are only handling them one at a time, and we are not caring at all about their order. And the reason for that is that Elm uses kind of a supervisor worker pattern in which one thread is the supervisor, and it takes care of the state, and it offloads all the work to the worker patterns, which will do whatever they need to do and come back with the state. So we have parallel I/O by default. But as I said, the supervisor is just one thread, so it's synchronous, which means that all of our state updates are synchronous. They happen one after the other, much easier to think about that. And because we have just one single state, one big value, all of our state updates are atomic. Even though we are using parallelization, we don't need to worry about state updates not being atomic. And you see, we are getting asynchronous I/O. We are using threads, we are updating our state, and we are doing all of that without needing to worry about mvars, threads, or software transactional memory. And we're using that inside of one simple, pure function. We're not doing anything fancy. We're using nice concepts, but we are keeping it very simple. So just to recap, this is how it works. We have our update, which changes our state, sends some messages to be something to be worked on by threads, which add messages to a message queue when they have finished with it, and eventually it will come back in the update function, and we keep this loop. Now, this architecture is great for organizing programs in general, but it's even greater if you have a user interface, especially if it is a declarative user interface. That means that a user interface that can be entirely described by our state. We can have a pure function from our state to, where is it? There we go. Our state to our graphical user interface. So this means that it becomes much easier to handle our user interface. However, it makes this pattern even more important because, imagine you have an input box and you want to type something there, and when you type it, you want it to appear on the screen. But if our user interface is entirely described by our state, then for it to appear on the screen, it must send a message to the message queue. Our one synchronous supervisor thread must handle it, update the state, and then the whole UI must be re-rendered for that character to appear on the screen. We must do that pretty quickly. So that's why the offloading of actions to different threads ends up becoming very important. If we're aiming for 60 frames per second, this all should happen in less than 16 milliseconds. So, and then this is one declarative view function. It's entirely described. We get our state and we output a string, which we could show in command line. The command line in this example here, I'm just showing all of the endpoints that were loaded, and then it will show whether it's a tuple, so whether they succeeded or failed or not. And then it's not all roses. It's quite a bit more verbose. Sometimes when you have messages that are related, so you have to do an IO action, change the state, and then do another IO action, change the state again. You have these messages, and it's not clear that they are related. I'm sorry for everyone that's at the back. So it's not clear that they are related, and that is a drawback of that. And also, every IO action needs to have a message constructor that handles it. So that's not as nice, but that's it. So with the Elm architecture, we get a list of events our program reacts to, very useful. Single state for the entire application. We get clear state changes. We get an explanation of why each change is happening. We get easy parallelization of I/O computations, simple atomic state updates, and great UI support, and all of that without getting very fancy. So That's it. If you want to see an example implementation of it in Haskell, you can go to this URL here, where there is one very simple implementation of mine. If you have any questions, I think I still have about 3 or 4 minutes to answer them.
Now I've got to go and get the mic and then bring it back to you.
So do you fork off a separate thread per each IO action, or do you have like a worker threads that handle those?
So in my implementation, yes, I do that, and the goal was to have it being very simple. It might cause problems, but the idea is that this problem is not necessarily tied to the architecture itself. It's an implementation detail. Yeah. So yeah, in my implementation, yes, I fork different threads, and you may also have seen that I'm just, for every page, I'm just forking threads to have HTTP requests for each link in there. In practice, that doesn't actually work because you would have too many HTTP connections, possibly. So you need to keep track of how many HTTP requests you have at any one time. So in this link here, there is an example of this full crawler, which is just 200 lines of code, and it has code that actually works properly and handles the threads adequately.
Thank you. So if I understand correctly, the IO messages are all done in parallel, but the update function itself has to be done on one thread. So does this mean you have to pay like close attention to doing most of the work in the IO message and not in the update function? And does that cause some practical concerns when you implement an application?
It depends on what you're solving. So most of the time, performance is not usually an issue. So this multi-threading thing, if you actually need something to be very performant, you would look at other ways to handle parallelism, and there are ways to handle parallelism with pure computations even. But if you do have problems, it makes it very easy to just offload those to different threads. But yeah, if you have a UI, for example, it's very important to offload things that will possibly take long to the other threads, because otherwise the main thread is blocked, and then the UI doesn't get updated, and it seems like your program is unresponsive.
I think that's all we have time for questions. Thanks again to Marcelo, and let's get Andor.